Okay.
Yeah, I'll let you know. This is just a recording. I'll let you know once we go live on Facebook.
Okay.
Okay, I'm crossing over.
Okay. Good afternoon, everyone. Let me just formally introduce myself. My name is Clarence Mokalapa, and I'm a lecturer at the University of Limpopo. Actually, today's lesson, we're gonna talk about the derivative as a function. And one may ask himself or herself, what is the derivative as a function? But in the previous sessions, one may note that we have looked at the derivative at a specific point. So let's start by let's consider a function, some function f of x, function f of x. In the previous section, we learned that we can find the derivative at the specific point A. For now, in this specific lesson, we're gonna look at our variable A is gonna be a change variable. However, it is not necessary to fix our point A. State A can be a change variable. So suppose that we have the specific point A, which is the changing variable. It means that our f prime of A, which is our derivative, is gonna be a change quantity as well. So therefore, this function f prime will be a function whereby the input, which is the specific point A, will vary, will change over time. So suppose that we want to replace this specific point, which is A, with x. So from the previous section, we saw that f prime of A is equal to the limit when h approaches 0 of f of A plus h minus f of A over h. But in the specific point and time, we want to replace this A with the variable x. So then we get this formula, which is f prime of x equal to the limit when h approaches 0 of f of x plus h minus f of x over h. And this is just the derivative. This notation is just the derivative of our function f. So this notation is read as follows. We say that this is just f prime of x, or we say sometimes they use f dash of x, but for my side, I prefer f prime of x. So let's suppose that we have y equal to f prime of x, which is our derivative. Then the output or the values of this y of this function f prime, this is just nothing but the slope of a tangent line. One can recall that in high school, what we have learned is that the slope of a function is just the change of y over the change in x. So this is the same concept, but eventually I will use a diagram to show you what do I mean. Okay, so before I go to an example, let me just go straight to the diagram and show you what do I mean when I say this is the same as we looked at the change in y over the change in x. Suppose that we have a function of this nature. Oh my God. Suppose that we have a function given by, oh my God. Suppose that we have function given by, this is our function. You will bear with me, I'm bad with drawings. Suppose this function is our f of x. This is our f of x. And suppose that we have here our f of x, suppose this y equal to f of x. So we have point here, we have point y2, which correspond to our x-axis, which is x2. And here we have x1, here we have x1, and then here we have y2, and this will correspond with this y values. So in our knowledge, we know that the slope of a function, which is the change in y over the change in x, this equal to y2 minus y1 over x2 minus x2, x1. Or in this case, what you will do is that you will go and replace our y2 with f of x2. So in this case, our y2 will be just equal to f of x2, because our y is just equal to f of x. And our y1 will be just equal to f of x1. So from here, we can replace our y2 and our y1, which is f of x2 minus f of x1 over the change in x, which is x2 minus x1. And one will note that if we, on this function, if we can sketch a secant line that will touch y2 and y1 like this, and call this point P and Q. Suppose that we can sketch a secant line like this. So suppose that we want this secant line to move, we want the point P to move closer and closer to point Q. Suppose that we want P to come here. For now, it means that our y2 will come here, will change. This is our new y2, and this will be our new x2 will come here. And this point will be P. So it means that this secant line will come, the P here will come closer and closer to our Q. Then we can come here and say that x2 minus x1 is equal to h. Because the moment x2, the moment this point P come closer and closer to P, to Q, then we can know this the change in axis is h. So suppose we want to make x2 the subject of the formula. So we're going to have x2, which is equal to x1 plus h. Then one will just come here and introduce the limit and say the limit when this h approaches 0, when the h approaches 0, because here when P come closer and closer to Q, then it means that x2 minus x1, it come closer and closer to 0. It will approach 0, which is our h in this case. So we can come here and replace our x2 as f of x1 plus h. Where there's x2, we are going to just replace it as x1 plus h minus f of x1 over, so we know that x2 minus x1 is just h. So this gives us our function, which is f prime of x, which is f prime of x1 in this case, because we are talking about x1. Okay, so let me go back to the presentation. Okay, so this formula, which is f prime of x equal to the limit when h approaches 0 of f prime of x plus h minus f prime of x come from the demonstration that we just had. So, and we say that this is just the definition of the derivative of f. This is just the definition of the derivative of f. So let's go straight to the examples. So suppose that we want you to find the f prime of x, where f of x is given by 2x cubed plus x. So we want you to find the slope of this, the slope of a tangent line of this function. So from the definition, we go straight away, we plug the definition. We know that f prime of x is nothing but is equal to the limit when h approaches 0 of f of x plus h minus f of x over h. This is just the slope of a tangent line, and we call it the derivative of f. So now where there is f of x plus h, where there is x here, we're going to replace it as x plus h for this part. And where there's x again, we replace it by x plus h for this x, minus f of x. This whole thing is just our f of x. Then now we can simplify. This is just simple algebra. We know that x plus h cubed is equal to x cubed plus 3x squared multiplied by h plus 3x h squared plus h cubed. This is just this part, x plus h cubed. And we know that when we remove the parentheses with a +1, we get x plus h. And here, when we remove this parenthesis with -1 multiplied by 2x cubed, we get minus 2x cubed. -1 multiplied by +x, we get minus x. So now from here, we can remove this parenthesis by multiplying throughout by this 2. So we get 2x cubed plus, one can see that 2 multiplied by this 3, we're going to get 6x squared multiplied by h plus 2 multiplied by this 3, again we get 6x multiplied by h squared, and again 2 multiplied by h cubed, we get this 2h cubed plus x plus h minus 2x cubed minus h. And one will straight away see that this and this will take care of each other. And again, this x and this one will take care of each other. This is symbol 1. You can see that these are the like terms. So we're left with 6x squared multiplied by h plus 6x h squared plus 2h cubed plus h. And one may look at our numerator here. One can see that we have a common factor, which is our h. So we may take h as common in our numerator. So again, one will see that this h and this h will divide. So we are left with 6x squared plus 6x multiplied by h plus 2h squared. And here we are left with 1. So again, when h approaches 0, it means that where there is h, we are going to replace it with 0. So when h goes to 0, but it doesn't mean that h equal to 0. It means that h goes closer and closer and closer to 0. So we are going to be left with, where there is h, we are going to replace our h with 0. Then we're going to be left with 6x squared plus 1. So in other words, our f prime is equal to 6x squared plus 1. This is our derivative on that function. But now we can conclude now we can conclude. We may use even diagrams. If we compare the two functions, one will see that from the cubic function, we have obtained a quadratic function. And one will see that this cubic function on our left-hand side, this function is x cubed minus x, and this function is x squared, is 3x squared minus 1, which is our f prime. So from our function, from our cubic function, so our derivative, it gave us our quadratic function. And one may note that from our quadratic function, if f prime of x is equal to 0, I mean here, on the turning point, if this is 0, it means that this function, which is our quadratic function, which is our cubic function, it has a horizontal tangent. It means that the tangent, remember the definition of a tangent is a line that touches our circle or touches our function once. So it means that here we're going to have the horizontal tangent. And when f prime of x is strictly greater than 0, it means that if our f prime is positive, it means here or here. If our f prime is positive, it means that our tangent of this function is a positive slope. And one may go and check this example in the textbook that we are using on this lecture, the Stewart textbook. So if our f prime is strictly greater than 0, it means that we are going to have a positive slope. Our tangent is going to give us a positive slope. So suppose that we want to again solve a function which is the square root of x, f of x equal to the square root of x, and we want to find the derivative of this function. We want to find the slope of a tangent line of this function. And again, we want to state the domain. One may look at this function and state the domain on this original function. One may see that all the negative values on this function, we may take it out. And we may consider only the positive values and 0 as well in the domain of this function. So, okay, so now we are going to find the derivative or the slope of a tangent line. So again, let's use the definition. So we know that the definition says f prime of x is equal to the limit when h approaches 0 of f of x plus h minus f of x over h. So by using the definition, we may be able to just straight away and substitute what is f of x plus h. So where there's x, we are going to just substitute here with x plus h minus f of x. F of x is just the square root of x over h. This is not a miracle, it's just straight substitution. So now when we are here, it is difficult to factorize or to simplify such function. And now we want to introduce the technique that will assist us to solve this. And the technique, we are saying that the technique is just to rationalize. So we are going to rationalize in order to eliminate the square roots in our numerator. Rationalizing, I mean that we are going to multiply by the special one. This is our special one, because if you check the square root of x plus h plus the square root of x divide by the same thing, this will give you 1. So, but this one, you must check what is going on here. One can note that from the square root of x plus h minus the square root of x, we just change the sign. When we multiply by this special one, the sign has changed from negative to positive. This is how you rationalize. And one will see that the laws of exponents tells us that if you have the same base, you might add the exponents. One can see that x plus h square root, it means that in exponential form, it means that we have x plus h to the exponent 1 over 2. So same base, then we're going to add the exponent. So x plus h multiply by the square root of x plus h multiply by the square root of x plus h. It simply means that x plus h to the power half multiply by x plus h to the power half. So this will give us x plus h to the power 1, because the laws of exponents tells us that if we have the same base, we may add the exponents. Similarly, the square root of x multiply by the square root of x. The laws of exponents tells us that if we have the same base, we may add the exponents. So it means that we have x to the power half multiply by x to the power half. So we may add the exponents. So that is why it gives us x to the power 1. So the one in the middle, if you multiply them, you will get 0. They will take care of each other. So from this step, one may see that if we multiply throughout by the special one, we are going to end up here. And now from here, we may go straight away and this in our numerator, this x and this x will take care of each other. So we are left with the h. And one may see that we have the h in the denominator. So this h will divide this h. So we are left with 1 over the square root of x plus h plus the square root of x. So now, because of we have addition in the denominator, so we don't have any problem. So we may just take it straight away when h approaches 0 and check what is our derivative. So when h approaches 0, we're just going to substitute our h with 0. And one will see that in our denominator, we are going to have the square root of x plus the square root of x. And when you add the 2, you will get 2 the square root of x. So it means that the first derivative, or the derivative of that function, or the slope of a tangent line of that function, which is f of x equal to the square root of x, is equal to 1 over 2 the square root of x. And because the question was saying we must find the derivative, and after that, find the domain of this derivative. So we saw that the domain of that function is all the positive numbers, including 0. But here, one may note that if we say the domain of this function is going to be all the positive numbers, including 0. At 0, we're going to have a problem, because we are going to have 1 over 2 multiplied by the square root of 0, which is 1 over 0. And when you press your calculator, 1 over 0 is math error, which is undefined. So it's going to be a problem. So in this case, we don't want 0 to be included. So that is why here, this will be all these positive real numbers, excluding 0 here, which are strictly positive. And here we don't include 0, because at 0, we have a problem. So here is the set of domain of this function f prime of x, of the slope of this function f of x equal to the square root of x. So now suppose we want to find the derivative of another function which is look like this, which is a quotient function. So again, straight away, go straight to the definition. The definition tells us that f prime of x equal to the limit when h approaches 0 of f of x plus h minus f of x over h. This is very important. This definition is very important, ladies and gentlemen, because this is just the fundamental principle of calculus. So if you know this, and then you don't need to memorize. So again, so now we want to go straight away and make some substitution. So from this function, one can see that where there's x for f of x plus h, where there's x, we're just going to put x plus h like this. And again, where there's x for this part of f of x plus h, we are going to just put x plus h again, minus f of x. F of x is the whole thing, which is 1 minus x over 2 plus x. The whole thing divided by h. And now when you are here, it's all about simple algebra. We know that from here, we are going to find the LCD or the LCM, the lowest common multiple or the lowest common divisor. And we simplify our numerator, and then we get this. One will see that both 2 plus h plus x plus h and 2 plus h are both our LCDs, and then you will say how many times 2 plus x plus h goes into our LCD. You will get the remainder is going to be this, multiplied by your numerator. And again, when you say this goes how many times into our LCD, your remainder is going to be 2 plus x plus h multiplied by the numerator here. So, and then this is your LCD, and you multiply by this h. So now it's all about simplifying our expression. One will see that when we simplify this, we are going to try to remove the parentheses. It means we are going to multiply 2 with 1. Again, we are going to multiply 2 with minus x. And again, we are going to multiply minus h with x, and do the same thing until we simplify our expression. So when you simplify your expression, you are going to get 2 minus 2x minus 2h plus x minus x squared minus x multiplied by h. And for this part, you are going to multiply throughout. 1 multiply this, multiply 2, 1 again multiply x, 1 multiply h, minus x multiplied by 2 minus x multiplied by positive x, minus x multiplied by positive h. So you will get this expression. And from here now, we may remove parentheses by this negative. So it means that positive 2 multiplied by negative 1 is going to be negative 2. And this minus 2 will take care of this positive 2. And again, minus 1 multiplied by x is going to be minus x. So minus x will take care of this positive x. And again, minus 1 multiplied by minus x squared is going to be positive x squared, which will take care of this one. And again, you have minus h multiply minus h and minus 2h. This will give you minus 3h. So minus 1 multiplied by minus hx, this will give you positive hx, which will take care of this negative hx. So in our numerator now, we are left with minus 3h. And one may check the h and the h will divide each other. So now we are left with, in our numerator, we are left with minus 3. and our denominator we're left with 2 plus x plus h into 2 plus x. But here we need to be careful. Please, in our denominator, don't multiply them. Just leave them the way it is. Because if you multiply them, you are going to confuse yourself. So please leave it the way it is. One will see that the reason behind leaving them the way it is because when h approaches 0, when you substitute h here, you will get the bases which are the same, and then you can apply the laws of exponents. Here, when h approaches 0, this part you are going to left with 2 plus x, which will be the same with 2 plus x. Then here we can apply the laws of exponents. Okay, so now our derivative or the slope of a tangent line of that function now is equal to minus 3 over 2 plus x, the whole thing squared. But we may say something about this. I don't see any problem. And one may go as an exercise and find the domain of this f prime of x. This is your exercise. Go and find the domain of this function. Again, there are other notations. There are other notations of noting the f prime of x. One may use this notation, which is dy over the x. One may use this notation as df over the x. One may use this notation as d over the x of f of x. One may use even this notation, start by a capital letter, d and f of x, or you may just say capital letter d with subscript x, f of x. So these are other notations that one may use in order to find the derivative of a function. For the next example, we are going to look at the absolute value function. We want to check if this function is differentiable. We want to check if this function is differentiable. And when we say the function is differentiable, it means that we can find the derivative of that function. We can find the slope of a tangent line. And we saw from the previous examples how to find the slope of a tangent line, how to find the derivative of a tangent line. So we say that the previous examples, those examples are differentiable. Those functions are differentiable. So let's check if the absolute value function is differentiable. One may note that in this function, when x is strictly greater than 0, the absolute value function is equal to when the absolute value of x is equal to itself x. And when we have an h which is smaller enough, which approaches 0, we may see that x plus h is strictly greater than 0. Here is the case, this is case 1, when x is strictly greater than 0. So we may say that the absolute value of x plus h, this will be equal to x plus h. So when x is strictly greater than 0, it means that the absolute value of x plus h is just equal to x plus h. Then by using the definition, we know that f prime of x is equal to the limit of f of x plus h minus f of x. So where there is f of x plus h, we are going to just replace it. Here we are going to just replace our x with x plus h minus our f of x, which is the absolute value of x plus x over h. But from what we have noted here, we said that when x is strictly greater than 0, it means that x plus h is just equal to x plus h. So here is the case where x is strictly greater than 0. So we have the absolute value of x plus h is just equal to x plus h. And again, we have the absolute value of x, which is just equal to x. And one may note that this x and this x will take care of each other. So we are left with limit when h approaches 0, we have h over h. And one may see that this h will divide this h, so we are left with 1. And you have seen from the previous sections of the loss of limits that if we have this situation, so it means that if we have the constant, it means that the limit when h approaches 0, we're going to get that constant back. So it means that at the end of the day, limit when h approaches 0 of h over h is equal to 1. This is case 1, when x is strictly greater than 0. This is case 1 when x is strictly greater than 0. So let's look at case 2 when x is smaller than 0, is strictly smaller than 0. So when x is smaller than 0, one may see that the absolute value of x, it will be negative x, it will be minus x. And then when h is smaller enough, when h approaches 0, we can see that the absolute value of x plus h, it will be minus into x plus h. It's when x is strictly less than 0. So by using the definition, we see that the limit when h approaches 0 of this absolute value, here when x is strictly less than 0, this is equal to minus x plus h. And minus, so when x is strictly less than 0, the absolute value of x is just minus x. And one will see that this minus 1 multiplied by minus x is going to be positive. And this will give us minus x minus h, positive x. And this x will take care of this x. So we're left with minus x, minus h in the denominator. So one will see that this h and this h will divide. So we're left with minus 1. Again, we have seen from the previous section that this will give us minus 1 at the end of the day. So it means that when x is strictly less than 0, our derivative is minus 1. When x is strictly greater than 0, our derivative is positive 1. So in this case, we are not finished because we checked when x is less than 0 and when x is greater than 0. So what about when x is equal to 0? So let's check when x is equal to 0. So let's check when x is equal to 0. So when x is equal to 0, again, by using the definition, it means that from the definition, we are going to just substitute our x with 0. And one will see that when x is 0, we just go straight away and substitute on the absolute value. Where there is x, we just put 0. So it means that here, the absolute value of 0 is just 0. And here we are left with the absolute value of h. So the absolute value of h over h. So again, when when h is strictly less than, less than 0, one will see that here the absolute value of h will be equal to minus h. And when h is strictly greater than 0, one will see that the absolute value of h will be equal to h, like this. So it means that here we are going to check at the left of 0 and the right of 0. So on the left of 0, the absolute value of h is minus h. And then we get what? Minus 1. And on the right of 0, on the right-hand side of 0, we get positive 1. This is a contradiction, because here we are at specific point 0. So on the left and the right, in order for this limit to exist, it must give us the same value. But here on the left, it gives us minus, and on the right, it gives us positive 1. So it means that f prime of 0 does not exist. We saw on the previous section what do we mean when we say the limit exists. It means that on the left and the right must give us the same value. So in this case, on the right of 0, it gives us a different value, and on the left of 0, it gives us a different value. So in other words, it means that the limit on point 0 does not exist. So therefore, we may say that this function is differentiable everywhere, except when we are at 0, because we saw that the limit does not exist at 0. So it means that it's not differentiable at 0, but it's differentiable everywhere. Okay, so now let's consider a piecewise function. Let's consider a piecewise function whereby we are going to look at the left and the right derivative and see if the derivative exists at that point. One can see that here the point will be 1. So it means that we have a function which is defined piecewisely. So when x is strictly greater or equal to 1, we have this function. And when x is strictly less than 1, we have this function. So we want to show if this function is continuous at x equal to 1. And we want to check if maybe this function is differentiable. But in this case, this function is not differentiable. So let's check why are we saying the function is not differentiable. In the previous section, we have learned about continuity, how to check if the function is continuous. And here I'm going to check if this function is truly continuous. So let's check at the left of this 1. At the left of 1, when 1 is strictly less than 1, when x is strictly less than 1, it means we are going to consider this function. So it means that the limit when x approaches 1 from the left-hand side, this minus here, it shows direction. It shows that we are talking about the left of this function, the left of 1 of this function. So at the left, we are going to consider this function, and one will see that straight substitution, we are going to have 1 minus 4 plus 2, which is minus 1. So it means that this function on the left of 1, we get minus 1, the limit of this function. And the limit of this function on the right-hand side of 1, on the right-hand side, this positive again, it shows direction. So it means that at the end of the day, on the right-hand side, we get -1 again, because on the right-hand side, the function that we are going to consider is this one, where x is strictly greater or equal to 1. So we are going to consider that function, and at the end of the day, it shows that it's equal to -1. So in conclusion, we may say that the limit, it exists because on the left of 1, it gives us -1, and on the right of 1, it gave us the same number, which is -1. So it means that the limit when x approaches 1 is equal to -1. And in order to check if the function is continuous, this limit when x approaches 1 must be equal to the function at that point. So now you are going to check this function at point 1. When you check the function f of 1, it means that we are going to check this function, because here it shows that x is strictly greater or equal. So when it's equal, it means that we are going to check this function. So when x is equal to 1, it means that our function is going to be -1. So therefore, we may conclude that since the limit at that point is equal to the function at that point, it means that this function is continuous at this point 1. Let me not emphasize on this because I assume that you have done this before. So now let's go and check for differentiability. So again, here we are going to use the definition, but here you must note that if you go back on my drawings where I have used x1 and x2, where we said the slope of change of y over the change in x, blah, blah, blah. So here I'm going to use that concept where we used y2 minus y1 over x2. In this case, this is just your x2, this is your x1. This is your y2, this is your y1. When x approaches 1. So again, it's just the definition of what we have seen. But here we want to check if this is differentiable at point 1. So it means that we have f of f prime of x equal to the limit when let's say when x approaches 1, because we want to check here of f of x minus f of 1 here over x minus 1. So here we want to check if it's differentiable. And we saw that from what we have done here, we saw that f of 1 is just equal to -1. So I may come here and substitute -1 on f of 1. But I don't know what is f of x in this point. So when I substitute f of 1, this negative and this negative, it will give us positive. So we have this expression now. So now we want to check from the left and the right of this one, maybe if this function is what? It's differentiable. So we are going to investigate here on the left of 1. So on the left of 1, one may go back to that function and check. On the left of 1, we are going to use this function, which is f of x. On the left of 1, when x is strictly greater than 1. So for f of x, we are going to use this function on the left of 1. And now it's all about simplifying. When you simplify this, you will get x squared minus 4x plus plus 3, 2 plus 1 is 3, and then you factorize your numerator. And when you factorize this, you will get x minus 3, x minus 1, and this will take care of each other. And one will see that we are left with x minus 3, the limit when x approaches 1 from the left-hand side. And at the end of the day, this gives us minus 2. When you substitute x as 1 here, you will get minus 2. So this is on the left of 1. So let's check on the right of 1. I mean that when x is strictly greater or equal to 1. So we saw that the function that we are going to use on the right of 1 is this function x squared minus 2x. And again, you may just simplify or factorize your numerator, and one will just check. This will be x minus 1 and x minus 1, which is just x minus 1 the whole square. So at the end of the day, we are left with this will take care of one of this. So we are left with the limit when x approaches 1 from the right of 1. I said this positive, it shows direction, minus x minus 1, and at the end of the day, we get 0. One may now conclude that since on the right of 1, on the left of 1, it gave us minus 2, on the right, it gave us 0. So it means that it doesn't give us the same value. So in conclusion, similarly with the limit, if the limit exists from the left and the right should give us the same value. So even in derivatives, from the left and the right we must get the same value. Such a way we may conclude that the derivative exists. But in this case, the derivative does not exist because on the left of 1, it gave us minus 2. On the right of 1, it gave us 0. So since the left and the right of one of this this function does not give us the same value, so we conclude that it is not differentiable at that point. The point at x equal to 1, this function, it is not differentiable. But we saw that this function is continuous at this point. So it means that if a function is continuous at a point, it does not imply that that function will be differentiable at that specific point. It might be continuous, but not differentiable. And we have seen this from this example. And if we take our function and we try to sketch it, one will see that this function is sharp at the point x equal to 1. And one will see that this is our function when x is strictly greater or equal to 1. Where is 1? 1 is somewhere here. So it means that this function is this one. And when x is strictly greater than 1, it means we have this function. It means it's this one. Okay, so now let's try to prove what we have seen already. That if function is continuous, it does not imply that the function will be differentiable at that point. Okay. So let's try to state this theorem. If a function f is differentiable at a, then it is continuous, but vice versa is not true. And the vice versa, one can say we have seen from the example that I just did. If a function is continuous at the point, it does not imply that the function will be differentiable. But if the function is differentiable, it implies that the function is continuous. And let's Let's look at the proof. We saw that continuity, we mean that the limit when x approaches a of f of x is equal to f of a. And we saw this is just what continuity means. If you can show this, it means you are done. And now we know that the function is differentiable. It means that if the function is differentiable, we know what this differentiable means. It means that from our formal definition, it means that f prime of a is equal to the limit of f of x minus f of a over x minus a. This means that our function is differentiable. This is from our definition. So here, from differentiability, this is what you need to just state. So let's check if it's differentiable. Does this function means it will be continuous? So suppose that we have f of x here, and then we add the special zero. The special zero, I mean that we subtract f of a and we add f of a. This is just the zero. There's no change. And suppose that x is not equal to a. So we may divide here, we may divide by special one, which is x minus a, x minus a. This is just the one, the special one I'm talking about. And now we may take the limit both sides. Limit when x approaches a. And now I may apply the laws of limits. It means that this is the sum law of limits. So it means this, I may take the limit of this plus taking the limit of this. So this is not a miracle. So now I may again apply the product laws of limits. It means that I may take the limit of this and again take the limit of this. So I will first take the limit of this, and the product law tells me again I can take the limit of this. And here the limit when x approaches a is just, this is just a constant, and we saw that from the laws of limits that the limit of a constant is just that constant. And again, one will see that this is nothing but the definition. This is nothing but f prime of a. This is nothing but the definition. Let me say x. This is nothing but the definition of our derivative. So because the theorem says if it's differentiable, so we have shown this is differentiable, so we must use the principle of differentiability in order to prove this. And one will see that if it's differentiable, it means that the whole thing, it means that the whole thing here is just f prime of a. And when x approaches a, it means that we are going to substitute a here, and we get this as f of a. This will give us 0, and at the end of the day, we are left with f of a. But remember, we started with limit. We started with, oh my God. Here we started with what? What we were proving here. Here we were proving that the limit when x approaches a of f of x is equal to what? Is equal to f of a. That is continuity. Continuity tells us that the limit when x approaches a of that function, if it's equal to f of a, then we are saying the function is continuous. So we have proved the theorem. We have proved this theorem that if it's differentiable, it means it's continuous. So it means it's continuous, but vice versa is not true. vice versa is not true. Therefore, we have shown this. We have shown that the limit when x approaches a is equal to f of x is equal to f of a. It's equal to f of a. And here we note that f of a is a relative, is a constant which is relative to x. It's a constant which is relative to x. This is just the constant which is relative to x. So at the end of the day, we have shown that f prime of a is equal to the limit of x approaches a, because this part does exist straight away from the theorem. And then I have emphasized that the converse of that theorem is not true. It's not true. It's not true. One may consider the example that we had, the one of absolute value. We have seen that the function was continuous at 0, but the function was not differentiable at 0. The function is continuous at 0, but it's not differentiable at 0. And this is some examples of where we can find the failure in differentiability. And we have a corner. A corner is when we consider the function of absolute value. The corner here, we may find out that this function at the corner is not differentiable. And we have discontinuity where the function is discontinuous. So it means that the differentiability fails. And then we have a vertical tangent, whereby an example one can look at this example, g of x equal to the cube root of x. This again is an example of where the differentiability will fail. And this is a vertical tangent failure. So now let's look at the higher derivatives. The derivative, the slope of a tangent line that we have dealt with, those previous examples, that was the first derivative. That was the first derivative. So let's look at the higher derivatives, whereby we have the first derivative and we differentiate again the first derivative. So from the first derivative, when you differentiate it, you get the second derivative. And when you differentiate the second derivative, you get the third derivative, and so on, and so on. Example, if you have f prime of x, this one is the second derivative of maybe the function y equal to f prime of x, f of x, and y prime prime is the second derivative of this function. And here one may find the first derivative. From the first derivative, then you differentiate again to find the second derivative. So if you have the first derivative, if they say find the second derivative of a function given, you may start by finding the first derivative. From the first derivative, then you may differentiate again to find the second derivative. So let's consider this. Let's look at this from the example perspective. Remember, we have find the first derivative of this function from our previous example. So let's find the second derivative of this function. For the second derivative, it means that we are going to differentiate this function again. Again, we may use the definition. From the definition, it means that where there is f prime of x plus h, it means where there's x here, we're just going to substitute x plus h, and again similarly, this one is just our f prime of x, is just this whole thing. So when you simplify this, you will get 6 into x squared plus 2xh plus h squared plus 1, this one, and then we may take care of this parenthesis. We multiply throughout by -1, and you get this. And one will see that again, if you multiply throughout by 6, this will give you 6x squared. 6x squared will take care of 6x squared. And 6 multiplied by this will give you 12xh. And this one will take care of this. And 6 multiplied by h squared, then you will get this. You will be left with 12x multiplied by h plus 6h squared in your numerator. And then here there's a common factor, then you may divide the two. And when h approaches 0, then at the end of the day, you have 12x. So this is the second derivative from that function. So we saw that we found the first derivative. From the first derivative, then we managed to find second derivative with these few words. Let me stop here.